Hi, in this video we are going to try and derive the cost function related to a Cobb-Douglas production function. Remember, we are working with the Cobb-Douglas function of this form. Q is equal to A times k to the power alpha L to the power 1 minus alpha. Now, the general form of a Cobb-Douglas function looks like this. A times k to the power alpha L to the power beta. Here I have assumed that this Cobb-Douglas function exhibits constant returns to scale, which means its degree of homogeneity is equal to 1. If you remember, in the very first property we had derived that the degree of homogeneity of a Cobb-Douglas production function will be equal to the sum of the powers of capital and labor. So, since alpha plus beta is equal to 1, I can replace beta with 1 minus alpha. So remember, right now in this derivation I'm dealing with a constant returns to scale Cobb-Douglas function. So this is the first equation that I already have. This is the production function according to which the firm is producing output. Now the cost function, as represented by the isocost line, will have the equation wage rate W times L, that is number of units of labor employed, plus interest rate R times K, which is the number of units of capital employed. Now, our intention in this property is to derive a cost function where we can express cost as a function of the total output produced. If you see in equation 2, cost is a function of the inputs K and L. Similarly, in equation 1, output is a function of the factor inputs K and L, or capital and labor. So we need to join these two equations in some way so that we can get cost expressed as a function of output. Now to do that, we will use a third function that is already known to us, which is the expansion path of the Cobb-Douglas function. So if your Cobb-Douglas function is of the form given in equation 1, then your expansion path can be written as alpha times W L minus 1 minus alpha times Rk is equal to 0. Remember, your expansion path, if you look at its diagram, gives you the relationship between the amount of input utilized and the quantity of output produced. Okay, so by combining these three equations, you can derive the cost function where cost can be expressed as a function of output. So if you notice, this is a simultaneous equation system. 3 equations, 3 variables, where variables are K, L and Q. Now, the next step, I'm going to multiply alpha times equation 2. So that will give me alpha times C is equal to alpha times WL plus alpha times RK. I'm going to name this equation 4. Similarly, I'm going to open up the brackets in equation 3 so that I will get alpha times WL minus R times K plus alpha times RK is equal to 0. If I name this equation 5, on adding equation 4 or let me subtract equation 4 minus equation 5. In that case, I'll have to change the signs. As you can see, alpha times rk cancels with negative alpha times rk. So I'm left with, and alpha times wl cancels with negative alpha wl, so that I'm left with alpha times c is equal to r times k. And from this I can write k as equal to alpha times c by r. This relation I'm naming relation 6. Now substituting the relation 6 in my second equation, that is the cost function wl plus rk, I will get c is equal to w times l plus r times alpha c by r. R and R cancel, and therefore I can write c minus alpha c is equal to wl, which wl, that's capital L. So L is nothing but 1 minus alpha times c by w. I'm going to name this or number this relation 7. And now putting relation 6 and relation 7 in, in equation 1, which was q equals to a k to the power alpha l to the power 1 minus alpha. So instead of k, I'm going to write alpha c by w whole to the power alpha, and instead of l, I'm going to use relation 7, which says it is 1 minus alpha c by, I beg your pardon, over here it is r, and relation 7 says that L is 1 minus alpha times c divided by w whole raised to power 1 minus alpha. Now if you actually open up the brackets, you will get this as a times alpha to the power alpha 1 minus alpha to the power 1 minus alpha c to the power alpha plus 1 minus alpha divided by r to the power alpha and w to the power 1 minus alpha. Once again, So as you can see, alpha and minus alpha cancel so that I have c to the power 1. Now remember, our target is to express c as a function of q. So I need the variable c on the left hand side, or as the subject of the equation. So keeping c there, I can write this as r to the power alpha w to the power 1 minus alpha divided by a alpha to the power alpha 1 minus alpha to the power 1 minus alpha into q. And this is the cost function of a firm which is producing according to the Cobb-Douglas function of this form. Now please remember that R is the per unit price of capital, and it has the exponent or the power that capital has in the production function. Similarly, W is the price of labor, and the power that it has is the same as the exponent of labor in the production function. If you remember that, then it is much more easier to memorize the formula for the cost function of a Cobb-Douglas production function.